Good evening, everyone, and welcome to the Amateur Radio General Class, session number 8. During our previous session, we looked at FETs, xenodiodes. We also talked about transistors, transformers, tapped inductors. We dealt with power supplies, components such as rectifiers. We also talked about the filters associated with the power supplies. Then we went on to discuss briefly digital circuits, what were logic gates, and we also talked about the D flip-flop and counters. And then we would have done our usual question pool review to match all of the theory that we would have covered. And then we had a little extra feature talking about space weather and power quality. So the agenda for this evening, we have a Q&A, and then we get into the technical topics for this evening. Oscillators, we'll discuss what are LC oscillators. Then we'll talk about the different classes of amplifiers, class A, class B, class AB, class C, and class D. Then we go on to discuss the formula for calculating RF amplifier efficiency. Then we discuss the concepts of self-oscillation and how to deal with it through a process called neutralizing. And then we discuss filters, low pass, as well as the concept of cutoff frequency. Then we deal with band pass filters, and then we discuss the concepts of ultimate rejection and insertion loss. Then we move on to talk about balance modulators and product detectors. Then the concepts of receiver sensitivity. Then we move on to talking about DDS, or direct digital synthesis, and DSPs, or digital signal processing. And we will end the theory talking about SDRs, or software defined radio, and the related I and Q signals. Then we will do our usual question pool review to match all of the theory that we would have covered this evening. All right, so just a reminder of the links for the technician class course. That's the level 1 course. Again, we're hoping that by now all students in the general class level 2 course that we are currently in would have had a chance to review the technician class course if you did not take it before. But again, we're putting up the links just in case anyone is now still joining the class or seeing it on YouTube and you want to know how to get to the technician class course. It's there as a slide for you. Right, in terms of our level 2 course, this is the general class syllabus that we're dealing with. And we are presently towards the end of the third topic, that's practical circuits. We shall finish that topic this evening so that next week we will begin the next topic of signals and emissions. So we are on practical circuits at the moment. Highly encouraged, take the practice exams. You have covered quite a fair amount of material, and now is a good time to see, just where you are with respect to that knowledge. So of course, doing the practice exams also gives you an idea of the questions, so that when you encounter the theory, you'll say, okay, this is what the answer is to that question that I saw in the exam, right? Again, persons interacting with React, the Zello channel, it's on your screen. Last week we put a quick link, so we're keeping the slide up. So in case you need a quick link to get to the channel, there it is in blue. Moving right along, we have the links to all of the material. So again, we do email out once a week at least to all participants, and including in that will be the current link to the video, but you also have a link to all of the videos recordings once they stick, as well as all of the material that would have been provided to students, including the slide deck. So these are important links for you to access the material, and should you wish to review any of the sessions. Of course, these are the texts that we can recommend. Students, if you would like to avail yourselves, feel free to purchase. They're optional. You can get them on Amazon or the author's website. Right, so let's deal with we do have a question from last session. So it was answered live in the session, but just thought it would be useful to bring a little bit of further insight into the question. So I think it was Arthur who asked the question, what was symbol 4 in the schematic, right? So this is symbol 4. And if we were to take a look at it, we will see that it resembles a diode. And I think when the question was asked, I did respond to Arthur to say that I believed that this is a varactor diode. So it is in fact a varactor diode, but the question is, what is a varactor diode? What is it used for? So we have a little definition as to what it is here on your screen. Essentially, the varactor diode is a component that changes its capacitance based on the applied voltage. So if you want to control the capacitance, you change the voltage going to it. And that's very helpful in tuned circuits where you want to change frequency or you want to adjust the resonant frequency of a circuit. You could do so electrically by changing the voltage applied to that varactor diode, and the capacitance changes. Remember, some if you have filter circuits as well. So LC, coils and capacitors, right? So that's what will change the frequency. So notice it's linked here to a potentiometer. So as you change the voltage, the capacitance changes and therefore resonance. So this is what a varactor diode looks like. We have a definition here. Note that it can also be called a varicap diode or a varactor capacitor, right? So very good question there, Arthur, and a little bit of extra information for the class, right? So, right, let's move right along. So just a reminder that we, from time to time, will use the electric circuit, water circuit analogy, right, to describe some of the concepts, because we are familiar with water at home, and electrical theory quite often mirrors in an analogous way the water circuit. So once you're familiar with water, electric circuit should be quite familiar to you as well, right? Okay, so let's get into some of the theory and the technical topics for this evening. So we're starting with the concept of oscillators, right? And an oscillator is a circuit, right? You could represent it on a schematic diagram as a circuit. But the purpose of an oscillator is to generate an AC or a sine wave output. So to generate that, we have a couple of components that comprise an oscillator. And if we were to look at the diagram on your screen, this is an oscillator, and we'll notice that we have an amplifier. We'll notice the signal that goes to the output is fed back into the input, and that's called a feedback loop. But it passes through a filter first, and those are actually components of an oscillator, right? So it will be an exam question on your right-hand side here. This is what you will get in the exam. What are the basic components of an oscillator? And it's a filter. So we have a filter and an amplifier, and it's operating in a feedback loop. So all that simply means is that the output of the amplifier, part of it is taken and fed back into the input. So some of those of you into automotive and know about turbochargers and so on, right? So sometimes they take a bit of the output and put it back into the input. So I guess similar concept, right? So that circuit that employs the amplifier with a feedback loop is called an oscillator. So just a bit of information for you to be aware of as well. The oscillator, the frequency within which it produces the oscillation, that frequency is determined by the filter. So you change the filter and you can change the frequency of oscillation. All right, so that's oscillators. So let's talk about another type of oscillator called an LC oscillator. So you're probably already seeing LC. That sounds familiar. L, we may remember as inductors or coils, and C, we may remember as capacitors. So we dealt with these during the technician class, and we also covered a bit of these concepts again in the general class previous sessions. So you are quite right if you were to say that L and C sounds quite familiar, because L is for the coil or the inductor and C for capacitor. So it just means that that oscillator uses an LC circuit. You have a coil and a capacitor, an inductor and a capacitor. And if we were to look at our diagram on screen, you will see here that there's a coil, which is an L, and a C. So that's why we say LC circuit. So in this case here, it's an LC oscillator, because we did say the filter is what determines the frequency output of an oscillator. And here we are using an LC type. So a coil and a capacitor, or an inductor and a capacitor. And together, these components form what we call a tank circuit, right? So that's the term, the technical term that we use. It's a tank circuit. That simply means it's an inductor and a capacitor. And this is the filter that we talk about that determines the frequency output of this oscillator. So you change the capacitance or you change the inductance or both, and you will change the frequency of the output of this oscillator circuit. So here's the exam question. The inductance and capacitance in the tank circuit determines the frequency of an LC oscillator. Verbatim from the exam. So the inductance coming from the coil or the inductor, and the capacitance coming from the little capacitor. Notice the circuit here. That determines the frequency of this output here, right? So the frequency of the LC oscillator. Okay. Now we come to discussing now amplifiers. Now, what is an amplifier? So an amplifier is something that increases the signal, right? Or you have gain, right? So you have an input and you have an output, and you expect through amplification that the output will be higher or larger or bigger or greater than the input, right? But there are different types of amplifiers, and we say that they are divided into classes. And each class of amplifier will have its own characteristics, or what it does, how it does it. And you may want to, as an amateur radio operator, if you're building an amplifier, you may want to choose the type of circuitry based on the properties of the different classes. So you may select a class A, or you may say a class C, depending on what your objective is. But we need to know what are the properties of the different classes. So let's go. So we see that we have a class A, we have a class B, we have a class AB. And if you're thinking, but wait a minute, a class AB might be a sort of hybrid between A and a B, and you'll be quite correct. It's a class AB. And then there's a class C and even a class D. So letters of the alphabet, A, B, C, D, right? So you have A, B, C, and D, right? So those are the different classes. But the class A amplifier, or when an amplifier is of type A or class A, it usually has high gain. It tends to be a high gain type of amplifier. And also it has very little distortion. So what that means is whatever the signal input is, the signal output quite much resembles the input, right? Except that it is stronger signal, or an amplified signal, but it introduces very little distortion, right? So we have some points here about the class A that you can take a look at. But we as amateur radio operators should know that a class A type amplifier is very suitable for AM and SSB type signals. And we say phone signals. Remember, in amateur radio, anytime we say phone, that means we are using voice as opposed to digital signals or computer that's generating the signal. We are speaking into a microphone. When we say phone signal, we are talking, right? So AM, amplitude modulation, and single sideband. Linear amplifiers or class A amplifiers are very suitable for that type of mode or that type of signal. A class B, well, it only amplifies half, but there's some distortion that occurs in the signal. Class AB is a balance between A and B. And then we have class C. So while it's not very linear, right, it is certainly more efficient than AB and AB. And as a matter of fact, we can say it has the highest efficiency. So it's not very linear, right? But it's good for specific types of modes. So notice we said the class A was good for AM and SSB, amplitude modulation and single sideband. Well, the class C is pretty good for FM, frequency modulation, and CW, continuous wave, also sometimes called Morse code. So you see, we have the different modes and the types of amplifiers that are quite suitable, or that you will select if you're building a circuit for that particular mode. So we need to talk about the class D as well. And class D is actually using what we call digital switching, or switching mode, using electronics to rapidly switch between on and off states. So you have class A, class B, class AB, class C, and class D. So now that we have spoken about the different classes, let's just quickly look at, the circuitry associated with the different types of classes of amplifiers. So again, this is not on the exam, but we like to give something extra, good to compare and contrast so that you can see, we're making it real here, that you can see the differences with the circuitry or the schematic diagrams, right? So one of the very useful things for amateur radio operators to be able to do is to read schematics. So that's why we have been presenting it on screen. Some of the exam questions are related to schematics because we expected to be able to read these drawings, just like a plan for a house or a building. You look at the schematic and we must get an idea of what is connected to what does it do? How can we apply it? That's applying the theory into practical ways that will allow us as amateur radio operators to use the electronics to achieve our objectives. So here we have the circuitry that matches. This is the class A type amplifier. We have the class B type amplifier. So you notice you have an input signal and you have an output signal and you have some components, right? You have resistors, you have transistors, you have capacitors, and so on. And some cases diodes, right? So you have the class AB here. And then you have the class C, and we have, well, the class D. So this is just to give you an idea. You could take a look at it on your own time and see the different types of components or what a typical amplifier circuit will be for the particular class. So not on your exam, but useful to compare and contrast to see that there's a difference in the circuitry or the schematic diagrams when you are comparing and contrasting the different types of amplifier circuits. So it's all on one sheet for you to take a look at. All right, so we come now to the exam questions associated with amplifiers. So all of these points, bullet points, are in fact on your exam, word for word, verbatim. So again, we did say that many times, not all of the time. So in this particular session, not all of the stuff that's in yellow is directly from your exam, but in this case, this slide certainly is. So you'd want to pay attention. So remember, in this course, we are doing light touch theory, but exam focus, right? So we want to make sure that you're duly prepared to sit and take and successfully complete the exam. All right, so first up, in a class A amplifier, the amplifying device conducts 100% of the time. That's an exam question. A linear amplifier, such as a class A, is described as an amplifier in which the output preserves the input waveform. That means that very little distortion, right? So that's linear amplifier, or class A. Then we have now class C amplifiers. They have the what? Highest efficiency. So we're just summarizing some of the points that we made on the previous slides, but these are in fact the exam questions. So we thought we'd put it on one slide for you so that you can look at what will be coming in the exam, right? And then also class C amplifier, right? So a class C power stage is appropriate for amplifying FM modulated signals. What other type of signal did we say? If you said CW, you'll be quite right. But in the exam, they will ask you, what will a class C amplifier be appropriate for? And the answer is an FM mode signal or FM modulated signal. Right, last bullet point on this slide. The efficiency of an RF power amplifier is determined by dividing the RF output power by the DC input power. So I have a slide coming up next that explains this last bullet point here, right? So let's say again, calculating the efficiency of an RF. What is RF? Radio frequency. We are amateur radio operators, or aiming to be, and that's what we're dealing with typically, radio frequency, and we want to improve our signal strength, so we use amplifiers. But how do we determine the efficiency? Well, we divide the RF output by the DC input power, and you'll see that in the next slide. So here we go. So this is the efficiency formula, pretty straightforward. Again, we say that the efficiency of an RF amplifier is calculated by dividing the RF output power by the DC input power. And this is the formula here on your screen. But let's take a moment to understand what this means and what this formula means. So I'm going to power, this is my transceiver, this is my radio. So what, as an amateur radio operator, I'm going to speak into, and my signal will go to the antenna, and another amateur radio operator will pick up my signal and hear it and hopefully reply, and we'll have a conversation, what we sometimes refer to as a QSO, a Q code, QSO in amateur radio. But we need to power equipment. So we can use a battery, or we may use something like a power supply or an adapter, right? Like this, to change the 120 volt AC that our house supply or a receptacle outlet provides down to 13.8 volt DC, which is what our radio needs. And we will output maybe 40 watts of RF power, 25 watts or 5 watts, and that radio frequency signal will leave the radio via a feed line or transmission line and go to the antenna, and it's radiated. All right, so we have electromagnetic radiation that's going out. But we need to know how efficient this is, and to be able to calculate that, we look at what the DC input power is going to be, and we look at what the resultant RF power output is, and we divide them, and we will get the efficiency. All right, so efficiency is equal to the RF output power divided by the DC input power. Fairly straightforward formula, right? Okay. Again, an exam question, as we saw in the previous slide. The efficiency of an RF power amplifier is determined or calculated by dividing the RF output power by the DC input power. So it's always output divided by input. Good. All right, so we now come to the concept of self-oscillation. So what is self-oscillation? So it's in reference to amplifiers. So we're amplifying a signal, but sometimes we have something parasitic, something that is unwanted really, called self-oscillation. It could cause distortion, it could cause interference, it could cause unwanted problems. That's self-oscillation. And what causes self-oscillation? So we have a circuit here, it's actually a tube circuit, but we could have also drawn it as a solid state circuit using modern components such as transistors and so on. But this is a tube circuit, so it's very relevant still, because quite often the amateur radio amplifiers that are used in today's world can still also be tubes, right? We have a lot of solid state electronics, right? Semiconductor based, but we also have tubes, as we dealt with a couple sessions ago. So this is a schematic diagram, and sometimes there can be self-oscillation. What happens is, due to stray capacitance or parasitic capacitance, you can have a bit of the output signal feeding back into the RF input stage. So some of the output comes back into the input. And remember, we said that that is oscillation, right? And if you, under right conditions, it can cause problems for you as an amateur radio. It's unwanted. So that self-oscillation can be caused by stray capacitance. But can you do something about it? Yes, you can. And that's why you're studying, that's why you're training, that's why you're learning the techniques and the theory associated with what can you do, what causes it, but most importantly, what can you do about it? So we can eliminate or neutralize that extra capacitance or stray capacitance in the circuit. And we do so by implementing, it could be capacitance, we introduce some capacitance inside of there that will cause that to be out of phase with the stray capacitance, and therefore they cancel each other. So we can neutralize that parasitic or that stray capacitance that's causing us problems, right? We just introduce a signal that is out of phase, and to do that, we introduce a component, and it could, for example, be a capacitor that causes that signal to be cancelled. So we can neutralize the effect of it, right? So that's self-oscillation and how we neutralize the self-oscillation. All right, so let's talk about some filters, right? So up on your screen, we have this trusty formula that you might remember when we dealt with decibels. We have it there for a bit of a reason, just to make some linkages between the concepts that went before. All right, so that's just there. But we're talking about filters. Now, there are different types of filters, right? And filters are all over and all around amateur radio circuits. And once you have a transmitting or receiving equipment, you tend to have a lot of filters, right? And filters are used to improve the precision of your amateur radio transmission and reception. It helps to filter, it helps to clarify, it helps to process your signal so that you get fidelity in the signal that you are operating with, whether you're transmitting or whether you're receiving. But there are different types of filters, and filters are applied in different cases. So we need to know a couple of them for the exam. So on your screen, we have examples of the different types of filters, and we'll dive a little deeper into a couple of them. But just compare and contrast, we have the low pass filter, and we have a graph that shows what happens in a low pass filter. You'll notice that we have the signal here, and then all of a sudden, signal drop off or it's attenuated. That's low pass, right? So the low pass means that the low frequency passes and the higher frequency does not. So that's what low pass means. You see, this is a low frequency, low, we're going higher, we're going higher, we're going higher. So the low, the signal passes until it starts to attenuate or drop off. So here the signal is not passed, right? So that's why we say the low pass or the low frequency passes. Then the opposite is high pass. So notice here, no low frequency passes until all of a sudden starts to go up here, and we notice that these frequencies are passed in the circuit, right? The filter filters out the lows and allows the highs, which is the opposite to the low pass, where it allows the low frequencies and filters out the high frequencies. So that's low pass filter, high pass filter. And then we have a bit of a combo. So we have what is called a band pass filter. So low part of the band is filtered out, it doesn't pass, but we have a middle section of the frequencies that are passed, and then the higher frequencies are filtered out. So that's why we call that a band pass. And then we have now what we call a band stop or band reject. So for example, here we have the low frequencies are allowed in, the sentry says, go ahead. And then the middle frequencies No, you're not going anywhere. And then as we go to a higher frequency, it allows. So that's why we call a band stop. So none of these frequencies are allowed through the gate. In this case here, these are the frequencies that are allowed through the gate, but below is not allowed, above is not allowed. So again, for low pass, these frequencies are allowed, they pass the gate, but the high frequencies don't. In the case of the high pass, the low frequencies do not pass, but the high pass are allowed through the gate. So again, these are filter circuits. And we are going to talk a bit more about the low pass filter and a particular property of the low pass filter. So this expanded graph comes from the low pass quadrant here. So this is the low pass filter that we have just expanded and labeled it a little more. But you should see the resemblance to the low pass. So here's the signal, it's allowed until all of a sudden it's not allowed, right? So the section that's allowed are the frequencies that are allowed. So remember, we are starting off at 0 or some frequency and it's increasing frequency on the x-axis, right? So on the y-axis, you have the signal level in dBs. So the frequencies are allowed, all these frequencies are allowed. Notice it's steady as you go. And all of a sudden now, it starts to attenuate or reject or reduce the signal to the point where these frequencies are not allowed. It's called the reject part of the graph. Where it allows it is called the pass, right? So it passes these frequencies and rejects these frequencies. So this is the frequency timeline that we're talking about here, or the x-axis, right? One type of filter is called a low pass filter. So we're dealing with the low pass filter, and it passes all signals whose frequency are below a certain frequency, and that's what we need to know. So below this frequency, it passes. Notice the graph is pretty high here. So all of these frequencies here, whatever those frequencies are, it passes, low pass. But there is a frequency above which it rejects, and we need to be familiar with that term. It's called the cutoff frequency. So it allows all the way up until here, it starts to drop, and at this frequency, we consider it to be the cutoff. But at what point do we consider it to be the cutoff? So notice here, it starts to drop, but ever so slightly, and then it drops and it drops and it drops. And then we reach a point here and we say, aha, that's the point at which it's now cutting off. But you will say, but wait a minute, it started to cut off before. Yes, it did start to cut off, but the cutoff frequency is at this point, and that has a special value. That is minus or negative 3 dB of the original signal, which is kind of half. And that's why we put up this trusty decibel formula. You may remember from the past that half power is 3 dB, right? So, or minus 3 dB, right? So if you double the power, it's plus 3 dB. If you half it, it's minus 3 dB. So when the power drops from the original signal to negative 3 dB, that's the point at which we can say, aha, that's the cutoff frequency. Not before. Yes, it starts to drop off before, ever so slightly. We have to wait until it drops to a level that's minus 3 dB. And at that point, we can say the frequency is the cutoff frequency. Again, note it's minus 3 dB or half the power. So once the signal goes to about half, that's the cutoff frequency with respect to the low pass filter. And we just have a little picture here. So what a practical example of a low pass filter in amateur radio might look like. Nice metallic box here, and you have your connectors at the end. These may be SO239 connectors that you'll put your coaxial cable to. And we'll have a little diagram shortly, next screen, next slide, where you'll see a low pass filter in line. All right. Let's do a couple more slides before we take our break. Right, so we're still talking about filters, right? Radio frequency filters, right? And this diagram here is just showing us we have inserted a low pass filter into this circuit, right? Why we might do that, you may ask. Well, sometimes an amateur radio transceiver or any transmitter may be outputting frequencies that are higher than intended, right? Those are called harmonics. And sometimes we want to filter out those harmonics, and the harmonics are multiples of the fundamental frequency that we are interested in. And our low pass filter will do that. It will allow the lower frequencies that we want to go to the antenna, but the higher frequencies that could cause, television interference and other harmful interference to other services, we want to filter that out. So it's low pass in that it allows the low frequencies such as HF, but it will block all of the higher frequencies. So this is an example. You have your power supply, you have your transceiver, you have a patch cord that goes to the low pass filter, and then low pass filter, you have some more transmission line that goes to your antenna, your HF antenna. And that's an example of how hams use low pass filters in practice. All right. All right, so let's just do a couple more slides again, and then we'll take our break. All right, so we talked about the low pass filter, and we did say we'll touch on another type of filter. So we want to talk about the band pass filter. So we said that this is the band pass filter here, and what did the band pass filter do? Well, it attenuates the low frequencies, and then all of a sudden it allows a range of frequencies, and then it cuts off again and doesn't allow. So it allows this band to pass through it, right? It says, okay, it's frequencies from this point to this point, you're allowed. Anything lower, you're not. Anything above, you're not. So we have now expanded this band pass frequency graph here a little larger, and we have labeled a number of things, right? So again, starting at this frequency, it's rejecting, it's not passing, that filter will not allow. And then all of a sudden at a frequency here, frequency 1, it will allow it to pass. And then it will again start to drop off and attenuate at this other frequency. So the frequency range between frequency 1 and frequency 2 is the frequencies that will be passed. And that's why it's called a band pass. So this band, or this section of the band, passes through the filter, whereas the others below it and above it is rejected. Again, filter may look like this, so it could look like something else, right? So a bandpass filter, it allows a range of frequencies to pass between, and it rejects the other frequencies outside of this range. And that's what this graph is saying here. Now, the width of the range and the difference between the two frequencies, frequency 1 and frequency 2, is called the pass band, right? So the width and difference between is given at minus 3 dB. So again, why minus 3 dB? Remember, it's half of the power, right? So that's how you know, or that's what you're looking for to determine where does the band pass start and where does it end. Once the frequency is at least half or minus 3 dB, that is what you're looking for. That's the point at which on the graph you're looking to identify, right? So notice again here, we say it's 3 dB. So this is the full signal here, it allows it, and then it goes to minus 3 dB, and therefore this is the reject section. And of course you have that also on the upward swing. And you may be asking, what's the difference? Well, what is it called if you were to, between the frequency 1 and frequency 2, it's called the bandwidth, right? So pass band, but the frequency range, if you were to subtract them, it's called the bandwidth, right? So you may say we have a 2 megahertz bandwidth or 500 kilohertz bandwidth or whatever. Once you subtract the two frequencies you get, that's considered the bandwidth. And this is also referred to as the pass band, because this is the band that is allowed to pass, but it's also the bandwidth that is allowed to go through. And it's frequency 2 minus frequency 1. All right, so let's see. Yeah, I think we could take another one more slide. Yeah, let's do this slide, or maybe 2 more slides, and then we take our break. All right. So we need to talk about ultimate rejection. So that's, no, it's not a band. It's a term that we use in amateur radio. And what that term refers to is a specification of a filter's maximum ability to reject signals outside its pass band, right? So we have another term that we also use called insertion loss that we need to be familiar with. So of course, once we put these components into a circuit, they have effect on the signal, and we need to be aware they can be lossy, right? They can, when you put them into, remember we showed you here on this diagram, normally we'll just connect our transceiver via transmission line to the antenna, but we have now introduced this extra component of a filter in between. So when we put these filters in, there's some loss associated with it, or the signal there's some attenuation, right? And it also depends on the frequency in use. But the term that we use to describe that loss, or that attenuation, or that reduction in the signal that as it passes through our filter, is called the insertion loss. And we have a little diagram here that shows the insertion loss for a particular filter based on the frequency. Notice that it's not necessarily linear, so we need to bear that in mind for a particular filter, how much signal is being lost or wasted by inserting. So it's a useful device, you know, whatever type of filter you need, but just bear in mind, it doesn't come for free. It often will attenuate or reduce your signal as well, right? So bear that in mind and be familiar with the curves that shows what loss, the insertion loss for the particular frequency. And if it's too high, then it may be unacceptable to you, right? So that's called the insertion loss. All right, so folks, I think now is a good time to take a short 2-minute break. Let's get up, take a stretch, have some water, maybe a bathroom break, and we'll be back in 2 minutes time. All right. Yes, good evening to you, Adish. Great to have you there. All right, so welcome back, everyone. And we are still dealing with filters, right? So we said that filters, there's a price to pay for inserting them. Yes, you want them in your circuit to reduce interference, to improve your signals, but there is the concept of loss or insertion loss or attenuation that may occur when or will occur. And it depends how much on a lot of things such as the frequency in use. It may cause too much attenuation or too much insertion loss, right? So you may want to use a different filter for the application or design things a little bit to take into account. You don't want your signal to drop so much that the filter essentially stop your circuit from working, right? You don't want that. You want it to be appropriate. So hence the specifications of these filters are important. You need to be aware of the frequency that you're using. So let's continue. All right, so we have some exam questions in relation to filters. So again, on the top here, we're just reminding ourselves, we'll be dealing with low-pass filters and band-pass filters, right? So this is what a filter may look like. Could take on very, very many form factors, but this is what it may appear to be in practical terms. All right, so let's go with the exam questions that you'll be getting in relation to filters, at least some of them. Then we'll continue a little more theory on the filter. So first of all, we did discuss this, the frequency above which a low-pass filter output power is less than half the input power is called the cutoff frequency. So remember we said that minus 3 dB, right? That's where the cutoff frequency occurs, that's about here. So that's an exam question. Less than half the input power for the output power is the cutoff frequency, all right? Also, the two frequencies that a bandwidth of a bandpass filter, so we're dealing with this graph here now, the two frequencies, this is frequency 1, frequency 2. The bandwidth of a bandpass filter is measured between the upper and lower half power. So what do we mean by that? You have to go to 3 dB or minus 3 dB from the maximum output here to determine where the frequency cutoff starts and ends, right? So this is the bandpass filter. It's the upper and lower half power. So about here and about here. So those are the two frequencies that we're talking about for the bandpass filter. And then we need to be familiar with the term ultimate rejection. And that term specifies a filter's maximum ability to reject signals outside of its pass band. So ultimate rejection. So if we were to look here, this, for example, the bandpass filter, this is the pass band. Anything outside is outside of the pass band. So for example, the low pass filter as well, anything within here is the pass band, and anything outside is not part of the pass band. So a particular filter, and it's a quality of the filter, its ability to reject signals outside is called ultimate rejection, and it speaks to the quality of the filter. And then insertion loss, it's a term that specifies a filter's attenuation inside its passband. So what do we mean by that? So let us say this bandpass filter, between frequency 1 and frequency 2, we wanted to pass these frequencies. But how much these frequencies are reduced or attenuated is the insertion loss for this particular filter, right? Because we want the filter to operate and be useful within this frequency range, but it's introducing insertion loss, right? But the frequencies within which the insertion loss is important to us is during or the period of the pass band, right? Which is all here. In the case of the low pass filter, this is the pass band. So we are interested in what the insertion loss is here. In the case of the high pass filter, for instance, we'd be interested to know how much loss occurs on these frequencies. This is what is called the filter's pass band. And in this case here, where the band stops, similarly, this is the pass band, or here's the pass band, and this is where it filters. So we want to know for these sections here where the frequency passes, how much insertion loss occurs at these frequencies. And you can usually get those in graphical format from the manufacturer of the particular filter. So let's talk a bit about transmitters. So we did say that we use filters in receivers and transmitters and so on. So we'll come to receivers in a little bit, but let's talk about transmitters. When we have a transmitter circuit, such as what you see on your screen here, right? This is an SSB transmitter. We have the various stages. You have the oscillator. We call a mixer. We have the audio that goes into it. And then we notice here, this is a transmitter. We notice that we have a sideband filter. And the reason we have a sideband filter in this type of transmitter is because we want to have a single sideband output. So we must have a filter. So this filter is an example of one that we introduced into a transmit circuit to be able to create the single sideband output. So we filter from this stage to get the single sideband, and of course then it goes to the next stage, the amplify, and then a low pass filter again. So there is something called the sideband filter that takes the output from the mixer, sometimes also called a balanced modulator, and that is what allows us to create this single sideband output from the stage of the transmitter. Now, what the mixer does, now again, the mixer in a transmitter is also referred to as the balanced modulator, and it takes, you have an oscillator. Remember, we define what an oscillator is. It produces a sine wave, and we take that sine wave at that particular frequency, and we introduce our voice, for example. Now, this could also be a digital signal. A computer is generating a digital mode signal. But let's imagine it's a microphone that we're speaking into. We have the audio amplifier stage, and it goes into the balanced modulator, also called the mixer. And combined with the sine wave or the frequency, remember we said we are modulating, we're using our voice, and we're going to modulate an RF carrier. And the RF oscillator creates that sine wave, and the mixer or balanced modulator combines them and produces an output. And in the case of a single sideband transmitter, you have a sideband filter that will strip off that is not necessary and just be interested in the sideband of the particular signal. So for example, here we have the sideband or SSB, single sideband. So we have the balanced modulator, it combining the audio frequency signal. This is the audio frequency signal that's coming in here, or voice, with this signal from a carrier RF oscillator. So we have the RF oscillator here that is creating the sine wave, and it is mixing. Now the output of the balance modulator, again, we call this balance modulator. We use the term mixer also interchangeably, so be aware of the two terms. We have both the upper sideband and the lower sideband. But if you want to filter out the single sideband, you have to use that filter to filter out the sideband that you don't want. Okay, so let's go to the next slide that talks about the opposite now, which is receivers. So you'll see that in this case here, we are using filters in transmitters. So hopefully this is setting the context for us to understand why are we talking about filters? Where do they come into our amateur radio circuits? So we're showing here block diagrams to show where filters are used in transmitters, and now we're coming to a slide to talk about filters that are used in receivers. All right, so we have different stages for different types of receivers, but we'll be just sticking to one is called the super het type of receiver, and this is very much popular for use for AM, amplitude modulation, as well as single sideband or SSB, and even CW, right, which is a form of AM. So if we take a look at this block diagram here, you'll see various stages in a receiver. You have the antenna, and then you have the different stages that the signal will go through and is processed to the point now where it leads to an audio output, and this is why you'll see a speaker on the end of the chain. So it's coming in radio frequency, it's being processed inside various stages, including mixing, amplification, filtering, and so on, and then demodulating to the point where you have audio that is delivered to the speaker. And we have an example of the various signals. So we start off with the radio frequency signal. It comes on in. You have the intermediate stage. It's mixed via an oscillator to create that IF frequency. It's amplified, and then we strip off now the audio component via the detector, and then we amplify it to go to the speaker. So this is signal processing of the received signal that you get towards the speaker, and this is why it's called a receiver. You're getting the signal, radio frequency signal, and you're listening on that frequency so that you can hear who is speaking, what they're saying, and these are the various stages in the super heterodyne receiver, sometimes called the super het receiver. And what that receiver does, it converts the energy coming from the radio frequency wave to an intermediate frequency using what is called the mixer stage, right? And then that mixer, it takes the incoming signal along with a local oscillator, sometimes called the HF oscillator, and it produces the intermediate frequency, right? So you have whatever megahertz is the frequency you're listening to, maybe 14.300 megahertz. It will down convert it, this mixer, using the input as the frequency you're listening to with the local oscillator, and produce the intermediate, or sometimes called the IF stage, or intermediate frequency. That'll make it a lot easier for the circuitry to handle rather than this much higher frequency that is coming into the radio, right? And that's what this local oscillator does. In fact, what it does, you want all of your filters and the stages after this to be produced at a cheap rate. So what you do, you don't want the IF stage to be able to listen to multiple frequencies. So what this local oscillator does, it has a property by when it mixes with whatever the RF frequency is, it produces the same intermediate frequency and the output, so that you can have a very nicely tuned circuitry that comes after it at the IF stage, right? So that's why it's called an intermediate frequency or IF stage. And you can also have what is called a product detector, and that will now demodulate the signal that's from the IF stage to give you the audio stage, right? So you have a BFO, or what is called a beat frequency oscillator, and you get the audio, and you are listening now to that transmission. So you have your receiver tuned to a frequency, and you're now able to listen to it because it has gone through the various receiver stages of mixer, goes to the IF stage, and then you have the product detector, and you get your audio output. So these are the stages of a receiver. And below here, examples of the waveforms of the signals as it passes through the various stages in the block diagram. Right, so continuing on receivers. So we did discuss specifically some of these stages. We have highlighted them here for you now. Again, try to strip off some of the concepts that we just discussed and hone on into some of them. So we have the product detector here, and it takes a signal that comes out from the IF stage or the IF amplifier stage, and it uses the BFO or the beat frequency oscillator. And the result is to produce that audio signal that goes now to the audio frequency amplifier. So when you see AF, that means audio frequency. When you see RF, that means radio frequency. So these are the waves going in space. Radio frequency. Audio frequency is what you can hear. That's why it's called audio frequency or AF. And it amplifies it so that you can get a loud volume coming through your speaker, and you can use that volume control on the radio to increase the volume level so you can hear the signal or you can hear the transmission that you're listening to. And in the case of our super het or super heterodyne receiver, there are a couple of stages that must be present or will typically be present. At a minimum, you can have multiple stages as well. And quite often, the more expensive the receivers are, you tend to have multi-stage. But as long as you have these three stages here, it will constitute a super het receiver. You must have an HF oscillator, or sometimes called the local oscillator. You have a mixer stage, and you have the detector stage. So that's why we have highlighted them here for you. Those are the simplest combination to create a super het or super heterodyne receiver. All right, so let's get to some exam questions that you will get in your test. So the first one, again, we have just reproduced these block diagrams here. On the left-hand side, you have the transmitter. On the right-hand side, you have the receiver. And when, by the way, you may recall the unit technician class, we said, when you combine a transmitter with a receiver, you get a transceiver. But these are the block diagrams to show you the transmitter stage, and this is the block diagram to show you the receiver stage. But it can all be within one package or one device, and that's sometimes called a transceiver. We call it our radio, right? But we sometimes take it for granted. Back in the early days of amateur radio, it was not unusual for your transmitter to be in a separate box to the receiver, right? So these are the stages here for you to see it. It's simplified. Yes, believe it or not, this is highly simplified for us to understand the various stages of the transmitter and the various stages of the receiver. Okay, so exam questions. The output produced by a balanced modulator, again, remember a balanced modulator is also called a mixer, is double sideband modulated RF. Right, so we need to know this for the exam. If this is your transmitter and you have your sine wave generator, RF oscillator, you combine it, you modulate it with the audio from your voice and from the microphone, you mix it here, right, that's the balance modulator. The output that you get here is double sideband, and you have to pass it through, as we said before, the sideband filter to strip off and get the appropriate SSB signal, single sideband that you need. But coming out, the output from here is double sideband. Let's just go back to that diagram so you can see it. So here's the double sideband, lower sideband and upper sideband. That's what you get. And the output of the balance modulator, sometimes called the mixer. Okay, so filter circuit, we spoke about this filter circuit, what we do with it. And it is used to select one of the sidebands from the balance modulator. So just another way to represent it. That's what the filter is doing. It is stripping off one of the sidebands just to leave the other sideband for you. That's what the filter circuit is used for in a single sideband transmitter circuit. Now we come to the receive stage, an exam question related to the receive stage, and that's the product detector. So we showed you where the detector or the product detector is, and it is used in a single sideband receiver to extract the modulated signal. And what that means is the audio. So That's why we need to be familiar with the technical terms, right? And concept, it might be straightforward, but they use technical terms to describe it. So the product detector, which is this, it is used in a single sideband or SSB receiver. So this is a receive circuit block diagram, and it extracts the modulated signal. What that means, it strips off the audio and sends it to the audio frequency or AF stage so that you can hear it. So these are the exam questions in relation to the receive and transmit stages of a radio. All right, so we now come to an important concept, and this is one that amateur radio operators speak of quite often. You know, if you have a radio, how sensitive it is. So we say receiver sensitivity is an important specification for our transceivers or receiver stage. Right, so we have a definition here of what receiver sensitivity is. It is the ability of a communications device, that's our transceiver, to detect or pick up and properly interpret, meaning demodulate the weak incoming signals. Remember, these are radio frequency signals that are going through the air, space, and we are picking it up with our antenna, and they are relatively weak, right? They're electromagnetic waves that are in the air, and we are grabbing onto them, and we want to listen to the intelligence or the information contained therein. And that sensitivity that we speak of with the receiver indicates how low can you go, right, in terms of the signal that you can still listen to, right? So that's why we say how low the signal strength can be while still maintaining reliable operation. So this is just a bit of a definition for us to understand what sensitivity it is, what sensitivity is about. So there are a couple important aspects of receiver sensitivity, or what we call parameters, that determine the sensitivity, and there are three of them that we have on your slide. These are the parameters or the properties of a receiver that determines its sensitivity, right? So when designing circuitry, when manufacturers, or maybe you as an amateur radio operator, you may decide to build your own receivers. These are the things that you pay attention to in your design to get maximum receiver sensitivity. I mean, you don't want a receiver that cannot hear anything, right? You want it to be as sensitive as it can be. So the first one is the amplifier gain for the input. And that simply means that you want to boost that weak incoming signal. So the stronger the gain of that first stage amplifier, if you look here, you notice you see RF amplifier, the stronger that is, the better or more sensitive your overall receiver will be. So you want a good amplifier, good low noise amplifier as well. Right, so that's one parameter with respect to the receiver to make it as sensitive as it can be. And also the bandwidth of the demodulator stage. You want to make sure that the range of frequencies that it can listen to are appropriate for the particular receiver. So we refer to that as the bandwidth. If the bandwidth is not wide enough, then we may not be able to detect the signal or demodulate the signal as best as we can. So the demodulator stage bandwidth is another important parameter that affects receiver sensitivity. And the last one is the input amplifier noise signal. So if that input amplifier is noisy, then it's going to affect the signal. If that noise floor is too high based on the amplifier properties, then we will not be maximizing the opportunity to receive weaker signals, right? So these are the three parameters associated with our receiver that causes it to either be less or more sensitive. And just for comparison, we just want to talk about FM receivers, right? So we did show you what the AM or SSB or CW type receivers are, and also the transmitters. So we're just showing here, and you may come across it as an amateur radio operator, you'll hear about the discriminator. So anytime you hear that discriminator, so you know you're talking about an FM signal, right? So FM receivers have different types of circuits than the type that you use for AM, CW, and SSB. Remember that we refer to that type of receiver as the superhet or super heterodyne type receiver, right? So FM receivers are different. And in FM receivers, that detector, we call it the detector in the superhet, it's called the discriminator for FM circuit receivers, right? And the discriminator that we use in FM receivers will convert the intermediate frequency, or what we call the IF, to the AF, or what we call the audio frequency, which is what you listen to by the speaker. So again, just a little extra information for your knowledge. All right, so we have a couple of slides to go again, so we'll be going a little bit over time this evening just to cover the content, and then of course we have the question pool review to do. So please bear with us. So we're now coming to the concepts such as SDR and DDS, and let's just go straight into it. So, you know, in the early days, most transmitters and receivers were of an analog nature. And last session, we started talking about digital electronics and the use of ones and zeros and the properties associated with digital type signals, right? Using binary, we know our computer equipment today uses ones and zeros. Digital circuitry talked about the different types of gates. And of course, in amateur radio today, we still do use analog circuitry and analog signals, but digital now is very much in play as it relates to modern equipment in amateur radio. So we have a couple of concepts that we want to talk about, such as DDS, SDR, and so on, and we'll define some of these terms. Some of these are also on your exams, and you need to be aware with it and to keep up with the times, right? So a lot of amateur radio equipment today, you will hear that they are based on SDR technology, or you hear that these are digital radios, right? So let's go. DDS is short, or an acronym for direct digital synthesizers, right? Or synthesizer. And this is what determines the transmit or receive frequencies, right? So we have a little diagram here that shows DDS circuitry, right? You see we have the phase accumulator, and then we have the amplitude or the carrier amplitude squelch conversion algorithm. And we also say that DDS, or direct digital synthesizer circuitry, uses frequency oscillators, or variable frequency oscillators that are highly stable. And because they are highly stable, they are much more stable than analog circuitry. And as a result of that, they have improved properties. So that's one of the advantages in using digital circuitry or direct digital synthesizer circuitry. Much more stable than analog type circuits. So we say that an advantage of DDS, again, DDS is direct digital synthesizer circuitry, is that it allows for variable frequency selection with the stability of a crystal oscillator. So again, this here is our little diagram that shows DDS as a block diagram. Let's come to now what is all the rage in amateur radio today, SDR. So you'll hear Hams talking about, well, I have an SDR, right? That can mean several different things depending on who you're speaking to. But let's talk a bit about the conceptual view of SDR, software-defined radio. So you'll say to yourself, wait a minute, software-defined radio? Well, yes, it's using computing technology or digital techniques in radio. So whereas before, radio tended to be all just hardware. In today's world, you have electronics. Sometimes you can have a computer that is doing that digital signal processing, right? So hence the reason software-defined radio. What it also means is the older analog circuitry tended to be fixed. If it's software-defined radio, that suggests that you can upgrade that software code to change what that radio is going to do. And yes, you'll be quite correct. It's software defined. So we can always change the software. Back when it was just hardware only, it was much more difficult. Yes, sometimes it was possible to update chips. You could pluck out a chip and replace the chip and so on. Some of those chips were tended to be updatable chips as well, such as EEPROMs and so on. But in today's world where they are software defined, you can actually upload a newer version of the firmware or that software, or use a computer with the software to do the modulating and demodulating of the signal. So hence the term software defined radio, abbreviated as SDR. And sometimes you'll see that a transceiver uses SDR technology, and it just simply means that the signal is being processed using that digital techniques and use of software as opposed to hardware or electronic components only. It uses software. So the term used to describe such equipment is SDR, or software defined radio. And we have a couple of block diagrams to show you receivers and transmitters, circuitry associated with SDR, just for your information. So you see block diagrams showing the various stages of SDR, or software defined radio, right? So you have analog to digital converters, digital to analog converters, and so on, right? So you can take a look at this and see the various stages of SDR equipment. All right. So we need to know a couple things about SDR, right? So first of all, because it's SDR, or software defined radio, we need to be aware the property associated with SDR radios is that it uses what we call I and Q signals, right? So it uses two signals, and those two signals are 90 degrees out of phase. So you have the I signal and the Q signal, and coming up in the next slide, we'll show you what we mean by the two signals are 90 degrees out of phase. So it's upcoming slide. So when an SDR is receiving, it is the receiver's analog to digital, or what we call sometimes A to D, analog to digital converters, that converts the incoming signal into those ones and zeros, or series of values, and those are what represents the I and Q signal. So you'll see a slide shortly showing that those two signals are 90 degrees out of phase. Now, when you're transmitting, it does the reverse. It uses those digital representations, the ones and zeros, of the I and Q signals to produce an RF output. Also, be aware that there's an advantage of using the SDR signal, or the I and Q signals, in that you can literally generate any type of mode or modulation that you need using software. So if a new mode comes out in the morning, you don't have to worry about changing the chipset necessarily. You just change the software definition of that signal, and there you go. So that's an advantage of using I and Q signals. You can manipulate those signals or modulate those signals accordingly using the software as and when you see fit. So that's why you will see sometimes software defined radios can deal with various modes quite easily, and even newer modes that may come about. It may be a lot easier to implement receiving or reception and transmission of those different types of signals. So software defined radio tends to be a lot more future proof than the older analog counterparts. All right, so I did promise you a slide to show what do we mean by I and Q signals being 90 degrees out of phase. So if you were to look at your screen, you will see this is the I signal, and you will see the Q signal, and you may notice that there's a difference. They are both sine waves, but these two are 90 degrees. So remember, from the full wave, it's 360, half of it is 180, and therefore a quarter of it is 90 degrees. So this is what we mean by the I signal and the Q signals are 90 degrees apart, or 90 degrees out of phase. All right, so let's go to the questions that you will get in the exam in relation to SDR, and you need to know this for the test. So we need to be aware of the functions that are performed by software in SDR. There are three functions. One is filtering. Yes, filtering. You're using that software to perform filtering. Because it's digital signals, you can process and filter using the digital signal processing technique. So filtering is one. Detection, yes, that is the other function that SDR software is used for, to detect the signal. And modulation, yes, if you are transmitting, you can modulate. You can take your voice and you could apply it to a carrier. The SDR software will modulate according to the mode. If it's FM that you're doing, if it is FT8 that you're doing, if it is CW, the software will generate the modulation to apply to the carrier. So these are the three functions that you need to know for the exams. For your exam, what are the functions performed by the software in SDR? Filtering, detection, modulation. All right. Next up, exam question in respect of DSP usage. An advantage of DSP's filters compared to analog filters is that it tends to have a wider range of bandwidths and shapes that can be created. So where you have the analog filters, they're pretty much fixed, and they tend to be hardware based. But the DSPs, which is software based, they tend to have a wider bandwidth, and you can change the shape of that filter accordingly using the digital signal processing techniques, or DSP. So you need to know about this advantage for the exam of DSP over analog. Wider range of filter bandwidths and shapes that can be created. Right, last bullet point, another exam question, and it relates to this diagram here. We talked a bit about it already, and that is the I and Q signals associated with SDR, right? So remember, once you talk about SDR, there are two signals, the I and the Q signal, and that is on the basis of which the digital techniques are used. So there's a phase difference, and the phase difference you can see here, you have this sine wave and this other sine wave that comes, it's 90 degrees out of phase. So the phase difference between the I and Q radio frequency signals that SDR equipment uses for modulation and demodulation is 90 degrees. So that's an exam question, and that's why we have this showing here. It's a 90 degree out of phase signal between the I signal and the Q signal. All right, so let's go straight to our question pool. See how quickly we can cover those exam questions related to our theory. All right, so let's see if we can speed through. We covered all of this this evening, so let's go. Which of the following are basic components of a sine wave oscillator? All right, so in other words, how do you construct an oscillator? We did say that you have a filter that determines the frequency, and you have an amplifier that takes the output and puts it back into the input in a loop. So that's a filter and an amplifier operating in a feedback loop, and that's the answer for what is an oscillator. Now we come to the LC oscillator. What determines the frequency of an LC oscillator? So we did say that tank circuit consists of the inductor and the capacitor is what determines the frequency that the LC oscillator operates at. So therefore the answer is the inductance and capacitance in the tank circuit. Next question in the question pool. In a class A amplifier, what percentage of the time does the amplifying device conduct? So let's dissect this question a little bit. What are they asking us? First of all, they're asking us about a class A amplifier. Remember, we had A, we had B, we had AB, we had C, we had D, right? So they're asking us about a class A amplifier, and they're asking us what percentage of the time does that class A amplifier conduct, meaning operate? Is it some of the time, all of the time, you know? It's actually all of the time, which is 100% of the time for class A. Next question, which of the following describes a linear amplifier? Well, it tends to be a class A amplifier, but what describes linear amplifier? It is an amplifier which the output preserves the input waveform. So there's very little distortion, right? So that's linear amplifier, preserves the input waveform. In other words, the output resembles very closely the input. All right, next question, which of the classes of amplifiers has the highest efficiency? So we did show that the class C of all of them had the highest efficiency. All right, sticking with class C. For which of the following modes is a class C power stage appropriate for amplifying a modulated signal? So we said it was the highest efficiency, but also it is used for FM. All right, so FM type mode or FM type signals. Next question in the question pool. How is the efficiency of an RF power amplifier determined? So we did show a formula that it was, you take the RF output power and divide it by the DC input, right? Get the efficiency. What is the purpose of neutralizing an amplifier? So we did say that sometimes in an amplifier circuit, you can have that parasitic capacitance that causes this signal of the output to be routed back in a loop to the input, and you get that self oscillation that occurs, right? So to counteract that, you neutralize it by inserting an extra capacitor, and it will cause that output to be out of phase with the one that's causing the self-oscillation, and it neutralizes it. So that's the purpose of the neutralizer, or neutralizing an amplifier, is to eliminate the self-oscillation from the parasitic capacitance. Okay, next question in the question pool. What is the frequency above which a low-pass filter's output power is less than half the input power? Let's dissect this question. What are they asking us? What is the frequency? So either some frequency or the name of that frequency. What do we call that frequency? But for what? Low-pass filter. So the output power is less than half the input power. So remember the low-pass filter, we showed that from 0 going all the way up to whatever that frequency is, it passes the frequencies, and then at a point it drops off dramatically and it rejects anything after that. So we did say that that frequency is called the cutoff frequency. Next question. The bandwidth of a bandpass filter is measured between what two frequencies? Let's dissect this question. What are they asking us about? Bandpass filter. So if you remember, the bandpass filter, it starts off not conducting the signal, it filters it out or it rejects it, and then all of a sudden it comes to a frequency where it allows the frequency to go through, and then it reaches another frequency where it drops off and the frequency is attenuated. Right? So what is the bandwidth of that? It's the upper and lower half power. So you look to see where minus 3 dB for both sides exist, and that is the bandwidth. What term specifies a filter's maximum ability to reject signals outside the pass band? So we did say that once you have a filter and you have the pass band, you have the reject section, there's a term that is used to determine that filter's property. It's also a quality of the filter. The maximum ability to reject signal outside of its pass band, that's called ultimate rejection. Next question in the question pool. What term specifies a filter's attenuation inside of its passband? Let's dissect this question. So we're looking for a term. A term for what? Attenuation. Attenuation that occurs where? Inside of the passband. So in other words, the passband is the frequencies that you want the filter to pass or to allow through. But sometimes, because you insert that filter in, it will attenuate that signal. That's what we're saying here. There's a term for that attenuation. It's unwanted, but it still exists and you want to minimize it. And it's called the insertion loss. Comes to the territory. Okay. Next question in the question pool. What output is produced by a balanced modulator? So we did show what a balanced modulator does. And we show that the output from that is actually the double sideband signal. That's before we filter it. So the answer to that is the double sideband modulated RF. That's what the balanced modulator product gives. What circuit is used to select from one of the sidebands from a balanced modulator? So we did say the balanced modulator gives double sideband, but in single sideband or SSB, we want one of the sidebands. So the output from the balanced modulator goes to that filter that filters out one of the sidebands to leave the other one. So the answer is filter. How is a product detector used? So we did say that the product detector is used in SSB receiver circuits to extract the modulated signal. So it strips off the unwanted signal. What you're trying to get is the intelligence or the audio, or what we call the modulated signal. So that's what the product detector is used for, in a single sideband receiver, to extract the modulated signal. All right. Next question in the question pool. Which parameter affects receiver sensitivity? So we did show a slide that talks about receiver sensitivity. What are some of the important attributes that we need to take into account that affects that receiver sensitivity? We listed 3 of them. They are the input amplifier gain. In other words, the stronger the amplifier, we're looking for it to be a low noise amplifier. That's the first stage from the antenna. We want that to be as high as possible. That affects the sensitivity. The stronger it is, the more sensitive the receiver will be. Also, the demodulator stage, the bandwidth of it, it needs to make sure that it covers the bandwidth of the signal that you want to demodulate. And also the noise figure, or the input amplifier noise figure. If it's a noisy amplifier, well, then it wouldn't be so sensitive. If the noise floor is less, you have less noisy the amplifier is, the more sensitive the receiver will be. And all three of these are in fact correct, so the answer will be all these choices are correct. Okay, a couple more questions. Which of the following is characteristic of a direct digital synthesizer? So we did say that the DDS, or direct digital synthesizer, variable frequency, variable output frequency with the stability of a crystal oscillator. So that's a property of a DDS, or direct digital synthesizer. You can vary the frequency and you have the stability of a crystal oscillator. Crystal oscillators tend to be very stable. All right. Now we come to next question in question pool. Which of these functions is performed by software in a software-defined radio? Okay, let's dissect this question. What are they asking us? They're asking us for the functions. Functions of what? Software. In other words, what's the purpose of software in software-defined radios, or SDR? What does the software do, or what can it do? Or what's the power of using software in SDR? First of all, filtering. Secondly, detection. Thirdly, modulation. And the answer would be all these are correct, because all choices, filtering, detection, modulation, are functions that software in software-defined radio performs. Next question in question pool. Which of the following is an advantage of a digital signal processing filter compared to an analog filter? So let's dissect this question. What are they asking us? They're asking us for an advantage, but of what over what? They're asking us for DSP, or digital signal processing filters, as opposed to analog filters. So what advantage do digital signal processing filters, or DSP filters, have over its analog counterpart? And the answer is a wide range of filter bandwidth and shapes can be created using DSP circuitry. All right. Last two questions. What is the phase difference between the I and Q RF signals that software-defined radio, or SDR, equipment uses for modulation and demodulation? Let's dissect this question. What are they asking us? They're asking us for the phase difference. So because they're asking us for the phase difference, the answer will usually be in degrees, right? So what is the phase difference? Between what? Between the I and the Q signals. Remember, in SDR, there are two signals, the I signal and the Q signal. And they want to know what's the phase difference between I and Q signals. So we did show a graph that shows that it is 90 degrees out of phase, right? That's a phase difference between the I and the Q signals for SDR. Last question. What is an advantage of using IQ modulation with software-defined radios? So we're asking here, essentially, what is an advantage of SDR, right? So it uses IQ modulation. What is an advantage? The main one is that all types of modulation can be created with appropriate processing. In other words, you can use software, you can change the code, and you could cater to modulate or demodulate all types of modes, right? So that's a distinct advantage of software-defined radio. So folks, that's it for our question pool that matches all of the theory that we would have covered this evening. So I know we went a little extra in time. We appreciate that. All right. So again, any questions, feel free to send an email to this email address. This is the mobile number that's good for WhatsApp. Any questions that you may have. Right. All right. Okay, so again, we have a WhatsApp channel. Feel free to join the channel. So we have a couple of questions in the Q&A. Given that we have kind of gone a little bit over time, we will deal with those questions the next session. So we will take a note of these questions, folks. All right. So feel free to join the WhatsApp channel for notification and also extra information that may be of interest to participants. And our next session, God's willing, will be next Friday, which I think is the 15th of December, usual start time, 8:30 p.m. 8:30 p.m. Okay, so folks, thank you very much for your time and attention. Do have a great weekend. Be safe. Do have a good night. Take good care.